Last time we talked about Shapley values, and just as a brief reminder, the Shapley values describe for a particular function and for a particular data point what the contribution of a particular feature or attribute is, and this happens with Shapley value in a particular nice formal framework. And by the way, of course, if we talk here about individual data points, you can, for individual data points, ask how important was an attribute in classifying this particular data point. You could sum over all the different data points to get the same information for a whole data set. And this is very interesting information. For example, I advise a PhD student who came up with this kind of scheme, and he did this on the one hand for determining explanation shift. What is explanation shift? When you build a data model, when you build a prediction model, and you have data on which you build it, then over time the data moves away from the model for which you have built it. This happens even very quickly. So in industry, typical times in the financial industry, maybe like 2 or 3 months, the data, the world has moved on to such a degree that you cannot use your old model again. The big challenge is to understand when is your model, the predictive model that you have, no longer good enough for your situation. When has the world changed so much such that the decision boundaries that you have are no longer valid? So the PhD student, Carlos Mugen, he came up with this idea to use Shapley values. So assuming that you train a classifier, that's your model, you then look for new data, how the Shapley values are distributed for a new data set that you have not seen before. And you compare these Shapley value distributions against Shapley value distributions from the data on which you have trained. And then if you find that these two different data distributions are such that the Shapley values differ, then you say, now I have to monitor my whole predictive model and think whether it's still up to date. And this is a very generic mechanism. Well, here's a bit more on how to do this then, but this is the basic idea. You can also do this for fairness. In fairness, you don't compare a new data set and a data set on which you have trained. But for fairness, you compare a data set about one specific group, let's say female, versus the data set on which you have trained, or the data set for another group, let's say males. And again, you would look at, are the two different groups treated the same, or are they treated differently? And you can find this, you can observe this by looking into the Shapley values. And it's not good enough to look into one data set because, I mean, for example, when you do a hiring position, you can hire only one person, let's say. There may be many reasons why you have hired this person, but when there is a systematic discrimination of a particular group of people, whether female or brown people, or you can imagine many different groups that could be discriminated, you can look at such kind of different treatments of whole groups of people. Yeah, that's here the equal treatment inspector, basically the same scheme, but with a slightly different arrangement of what I described. So finding explanations is useful and important in order to find such changes, either just for the quality and validity of your predictive model, or even for the comparison of treatments of different social groups. Okay, so much for the Shapley values. Now we get to the next model. We looked so far at bagging, where we looked at random forests to do some voting of individual decision trees. Now we get to boosting, and as I explained the last time, I said that what are the most successful methods in Kaggle competitions, boosting methods belong into this category. So when you have tabular data, then boosting very often is the default method to go to in order to solve your problem, in order to model your problem. We first talk here about decision stumps, because the idea is that when we do boosting, we take very simple decision models that are not satisfying at all, that have a very low quality, but are super efficient, and then we combine many of them in a suitable manner. So, what is our situation here? We start with training data, and here we assume here for this presentation that we have two classes, but actually the method that I will present first, then AdaBoost, was actually originally done for regression and not for classification. So there are always counterparts, and the idea is that you get familiar with one of the two problem areas, classification or regression, and when you then need the other one, you know the basic concepts, you can go and read this up yourself, and based on the experience that you have and the lecture content, you can easily acquaint yourself with the other paradigm. So here we have this classification problem. So for some vector of describing an object, we have yi's, which come from the one class or the other class. Now, a decision stump is a very simple function phi, and this is indexed. So we have d many decision stumps. And it has a polarity that's not described here, but down there, and we have a threshold. And so decision stump indexed by j to decide the different decision stumps with a threshold of s decides on an object x to which category it belongs by computing p, the polarity, which is either -1 or 1, times the sign function. And you know the sign function is 1 for every value above 0, -1 for every value below 0, and 0 for 0. So polarity times the sign function of simply the value in the jth component, so the jth attribute of your object x, minus the threshold for this particular stump. And that, of course, means that it's p if the value is larger than the threshold, and it's minus p otherwise, because the sign function will turn around the minus, we'll take it times -1. And when we do this, we get a certain error rate. So the error rate for this decision stump, how is this computed? Well, we go over all data points, data point 1 to n, and divide by the number of data points. And this is a test, and the test is either 0 or 1. And we check whether the test, this feature, this decision stump, makes a correct prediction. If it makes a correct prediction, then this is equal. That means that the inequality is not given, so it would be 0. And if it's different, then the error rate is increased. And, well, of course, instead of this decision stump, you can just take the definition of this decision stump, and since yi is plus or minus 1, we can just look at whether this condition is fulfilled and count how often this condition is fulfilled. And this gives us the error rate on such a simple decision stump. And now what we want to have, we want to find a decision stump, phi js, with the right polarity and, well, some index that looks at the different attributes, and with a threshold. And so among all the possible attributes, among all the possible thresholds, and for the thresholds, actually, we don't look at all the possible real numbers. we only look at those numbers that actually exist in the data set for this particular attribute. So that limits the number of numbers that we have to look at. So among all these many different decision stumps, we look for the one that minimizes this error rate. So it's not so difficult to do this computation. It's a bit of effort, of course. But it's a local decision because we can do it locally for any attribute. This is a learner, but it's a super weak learner with a very large training error. So here we visualize the situation. Let's assume here we have the data points for one class. Here we have in red the data points for the other class. So this is blue versus red. Then, for example, deciding that this is the one attribute dimension we are interested in, introducing this threshold in order to distinguish between red and blue would be a weak learner. But of course, it would all put all these different red dots here into the wrong class. But the idea is then that we do not only have one decision stump, but we combine several decision stumps. So we would also have on another dimension another such decision stump. And now you see already with the combination of two decision stumps, we can, in this very simple example, I mean that's way too much toy-like, separate the blue dots from the red dots. And of course we can extend that. We can extend that to nominal features, categorical features. We could even have functions that are a little bit more complicated, like very small decision trees, where we have maybe a few steps, have a certain depth of a decision tree, like 2 or 3. Okay, so this is just the preliminary that we need now and that we use in AdaBoost. So what is the core idea with AdaBoost? The idea is that we weigh the data and we weigh our feature functions in order to combine them towards an overall good classifier. What we assume here is, just to make the notation easier, an infinite collection of feature functions. So each feature function, maps from our object descriptions into either the one class -1 or the other class +1. We assume for this infinite collection an infinite vector of weights. Well, I mean, just for notational convenience. Actually, we assume that only a finite number here are non-zero. So it's just really, we don't care about a maximum size of that vector. So practically speaking, it will have a maximum size. And then our classifier that we want to achieve is this predictive model, f hat of theta, where we take the sine function and we add up all the feature functions in a weighted manner, because every feature function has a weight theta j when we provide such an object x. Yeah, and the sine function will give us either a -1 or a +1. That's our target. And what we can also do is we can even just write, okay, seems now I have no battery anymore. So let me try to point here. So we can also write this simply as a vector theta, and then theta transposed phi, where phi also is a vector of functions. So we just have this vector, inner vector product between the weight vector and the function vector. Now, given all that, what is now the idea? The idea is we have some training data, some training sample, and we start incrementally to add new feature functions and weigh them. So given this training sample, we create our first feature function with, for example, such a decision stump as I just showed you a few slides ago. Now, when we do this, we do mistakes, obviously, as you saw with these red and blue dots. We did many mistakes, actually. Now, the idea is that when we do mistakes, we want to focus on those data points that we misclassified. And so the misclassification is then changed, or the weighting of these data points is changed to make the misclassified one more important. And so we have a reweighted sample. We still have all our data points, but not all our data points then has the same importance. The correctly classified ones, we say we don't care about these so much. And the incorrectly classified ones, we want to improve or increase in their importance. And so as we go along, we permanently compile a new predictive model by adding these different feature functions on top of each other. And when a feature function is very good, we give it a large weight. And when the feature function is not so good, we give it a lower weight. And we tie this to the error rate. If the error rate is high, the feature function receives a small weight. If the error rate is low, it receives a high weight. And so we do this until we converge. So until at step M we have converged and our error is small enough for what we are interested in. That's the idea. That's the overall plan, which we now have to look at in detail. So how then, of course, to select the weights? The weights are the thetas, and how to select our feature functions. That's then the question for this model. So here is the discrete AdaBoost algorithm. So how important are our data points based on which we learn initially? They have uniform weights at the beginning. Every data point receives a weight of 1 divided by n, where n is the number of data points. And now we start such a loop that we pursue until we converge to a good enough quality. So we fit our classifier in our current iteration. So now the index number m will be increased step by step. And we have a current weight. As I said, initially this weight is uniform for all data points, but then it will change, and I will tell you how. We can compute the normalized weighted error. So what is the error for the current feature function that we have in step M? Well, it's simply the error that I showed you before. How often do we misclassify something? But before, we simply aggregated these errors and divided by n, with n being the number of samples. And now we don't divide by n, but we multiply each error with the importance of that error with our wi. And rather than dividing by n, we sum up all the different weights to get a normalized error rates, usually divided by n. But here, since we have reweighted everything, we divide by the sum of all the different weights. So initially, if wi is 1 divided by n, and we sum this up over all n, this would be a division by 1. Not super interesting, but of course when we increase the weights, then we'll have to normalize again. Now, what we do is we compute the odds and then the log odds. What is that? Well, here in the denominator, we have this weighted error rate. So if the error is high, then this should become a small number, because if our current feature function is not doing super well, we want to give it a low weight. Now, if this is the error rate, and the error rate is always between 0 and 1, because of the way we defined it. So if the error is small, like 0, then of course that means everything is correct. So 100% or 1 is correct. If the error is very high, let's say everything is wrong, then it would of course be 1 minus 1. Then we would have 0 correct classifications. So we compare the correct number, the correct samples, how often have I been correct with my prediction, divided by the number of incorrect ones, but not just the number, but the weighted number. And this gives me a fraction, and we take the logarithm of that fraction. So this gives us weights between minus infinity and plus infinity. And now what we do, that's a trick here, where I will then show in the next slides that this really works, is that we take the current weight and set the current weight to the weight times e to the power, the weighting here of our current, the weighting that we computed here, derived from the log odds, times the question whether we were right or wrong. And if we are wrong, this is a decision that returns a 1. And if we were correct, then this is a 0. So if we are correct, this is a 0, then it doesn't really matter what this is. E to the power 0 would be 1. So if we're correct, we don't change the weight. If we're incorrect, then of course it depends on this error rate that we had so far. But if we're incorrect, then this is a 1, and we take this error rate to modify the previous weight. And, well, let's assume we are not doing so well. Then this will be a value below 1. Yeah, if we have many errors, then let's say the error will be closer to 1. Then this will be a small number, and this will be a larger number, and this will be between 0 and 1. And the logarithm between 0 and 1 is, of course, somewhere between 0 and minus infinity. And so we then reduce the previous importance of this current data point. And we do so until we converge. And as an output, we simply take these weights from this consideration times the different feature functions that are all in this vector. So let's illustrate this. How does this then work more practically? We start with an equal weighted sample here. We have the pluses as one class, the minuses as another class, and now we look for a decision stump. And let's say the first decision stump is this H1, and based on this decision stump, we distinguish the positive class from the negative class. And now here we have circled the wrong decisions. And because these decisions are wrong, the weights of these data points are increased. So the pluses now become larger, and relatively speaking, the weights of the other data points are reduced. So that's why this plus is now smaller than before, and this plus is now larger than before, relatively speaking to each other, based on renormalization. So the idea here really is to say that when I use this decision stump, I really want now to focus on those data points where did I mistake. So with this new weighted data set, I really now try to get the pluses right. Let's assume I would do a decision stump H2 that would do this. Now, of course, we have new mistakes, namely these minuses here would be wrong. And so the minuses here become larger. The plus gets even smaller here because they were already right twice. And the minus here is also small, but these minuses here are important to classify correctly. And now I use H3 as my next decision stump in order to do this classification. And so you see, by adding these decision stumps on top of each other, we reweight until the mistakes at some point are taken care of. And then I combine this. I take the first feature function and the second feature function and the third feature function. And depending on our misclassification rate, I have the corresponding weights for these different feature functions in order to get a correct description of the positive and the negative classes. And here is some artificial data, namely assume in one dimension 10 standard Gaussians. You just pick some mean values for these 10 standard Gaussians, and within a certain environment around this mean points, it's a positive class, otherwise a negative class. And then you start to do decision stumps. And the first single stump you see has a super low accuracy or a very high error rate. So the test error is 0.45. It's almost a random decision. It's only slightly better than a random decision, which is not a big surprise, given that the data set is so complicated, so it's really just on one line. But when you now add more and more decision stumps, the test error decreases. Doesn't get perfect. Well, we always have some base error, right? Always have to consider that. There is always some confusion where you cannot really do any better. You don't know what the base error is unless you know explicitly the distribution. But one can expect that one doesn't get to a zero error rate. And when we now compare this, here we have the number of iterations for boosting, and every iteration, of course, corresponds to an additional new decision stump. Then we see we have here, for comparison, a decision tree with 244 nodes that with 244 iterations in our boosting, we do much better than the corresponding decision tree. So what we see is the single decision stump is hardly better than random, but these combined stumps are much better. Okay, so how and why does this work? Yeah, there's a question? Do you mean that when I increase this decision tree, that the test error would increase again? Yeah. That's to be expected when I don't do this carefully. Yeah. Because we would run into overfitting. So it is not a good idea to always increase the size of such a decision tree. We will overfit to our data at hand. For example, we will then do decisions. Let me illustrate this. Yeah, we have a situation that we have, let's say, positive classes here, negative here, negative, positive, negative, negative. And let's say this is a valid classification. But when we have, for the positive, such a Gaussian distribution, we have just an outlier from another distribution. And because of the Bayesian error, this Bayesian error, sorry, I have to sneeze. This Bayesian error, so our decision tree will try to fix this error if we're not careful. And with the decision stumps, we'll always take a larger set of instances into account. We don't focus on just a very small data set of a single instance. And that's the advantage that the other boost is quite good at generalizing here. Does this answer the question? How different is it from overfitting? I'm not sure what this question means. So this here is the test error. So in a test error, I mean, the overfitting means that we decrease the training error, but we increase the test error. And since this is the test error, we see that we don't overfit here. How are we generalizing it so well without doing overfitting? I have a slide which talks about a situation where we run into this issue, but it's about maybe, I don't know, 10 slides from now. If you maybe wait for this, and then there can be situations where we don't do very well with boosting. Okay? Okay, but for now, let's continue and remember your question. If it's not answered at the end of the lecture, please ask again. Okay, so let's try to understand AdaBoost. So what do we do here? We have an additive model. What is an additive model? It's simply a sum of base functions. Here the base functions are called B. You could imagine them to be decision sums, but indeed it could be other base functions. And if you think of other kind of mathematical approaches like discrete cosinus transformations or so, you have a similar thing, right? You really have a base function with some parameterization and a weighting. Yeah? Discrete cosinus transformation looks similar. So we have an additive model with a base function and, for example, decision stumps here, and this decision stump is has a parameterization beta. Every stump has another one. And every stump has a weighting. So we have these expansion coefficients, as they're also called, and the parameters. And this together gives our predictive model. Here are other examples of such additive expansons. Signal processing, wavelets, sinus functions, all these can be used for such additive modeling or particular kind of splines, Bézier splines, etc., etc. So now in general, of course, when we have this function, we could say, okay, let's optimize this function. That, of course, would mean we would optimize all these parameters at the same time. This is very hard. So, I mean, typically strategy is when we have such a hard problem, let's do it greedily. Let's do it one by one. And that's what's done here. Optimizing everything is too expensive, so fit one basis function at a time. And if you remember the AdaBoost scheme that I just presented to you a few slides ago, that's what we did. So we start with 0, and then we repeat. What we do is we try to minimize a loss. And the loss function comes from the class assignment for our current data point. Look, here we go from data point number 1 to data point number n, all the different data points that we have for training. And we have this loss function, which depends on the class of that data point, which depends on the modeling we have done up to the point m-1. Up to the point m-1, we have used such an additive model, because we go from 0 to 1 to 2 and so on. So we incrementally optimize this function, and the function f hat m-1 includes everything from f0 to fm-1 in a weighted and added model. Okay, so here our model so far gives us a certain loss, of course, or makes a prediction, I should put it like that, makes a prediction that leads to some loss. But the prediction that we have so far is then enriched by the prediction of the base function with a new parameterization and a new weight. And these beta tilde and theta tilde will look for the ones that minimize this overall loss, given that I have my prediction and I now extend this prediction by one additional base function, just like the AdaBoost scheme before. So Fm hat, our new predictive model, is then the previous predictive model, which is now improved because we add this. And remember, we have now used the one that best reduces our loss, that makes the error as small as possible, as we can do in one step. Remember, we have base function. It's very easy always to think of decision stumps. It could be other base functions. So how can we now connect AdaBoost and forward stage-wise additive modeling? Well, that depends on the loss function. And the loss function that we use for AdaBoost is exponential loss. And the funny thing was that AdaBoost was invented in the late 90s. Yeah, I heard some tutorial by, I think it was by Freund or Shapiro, one of the two, at the ICHCAI 99 in Stockholm. And at that time, people didn't even know that the AdaBoost scheme would actually use an exponential loss. It took the community 5 years to find this out. Yeah? Sometimes you make progress and then people see it's useful and it works well, and then people investigate the theory and so on. So the question then often is, it works in practice, why does it work in theory? Yeah? But this may help. And then now what I present to you and then show is that the loss function we use here between our class and the predicted value, or could be regression, then would be the numerical value and the predicted value, is the exponential loss. And what is the exponential loss? It's e to the power minus y times f of hat of x. So let's assume the y is either +1 or -1. And let's assume f hat, let's say y is +1 and f hat is very large. Then they agree. F hat says it's really this class +1 and y is +1. Then this is a very large number. Because of the minus, it becomes a very negative number, and e to the power of a very negative number is a very small number because you have exponential decay, which means you have a very small loss. The same is true if y is negative and f hat is a very negative number, you have a very small loss. If the two diverge, then you have e to the power a positive number, which grows very, very quickly. So you have a large loss. So this is the exponential loss, how it works, just by looking at the algebraic terms. Now, what we want is, we want those parameterizations, the weights and the parameters of our base function, that minimize this exponential loss. And the exponential loss is just like this one here, but because we now set in our specific model composed of everything we have done up to the point m-1, plus our new additional parameters. That's why it looks like the term here. And of course for all the data points from 1 to n. Here, by the way, a short comparison of the exponential loss. And what is not really visible here is that the prediction here is really the y times f hat of x. This is on the x-axis. And when this grows, becomes very large, then because of exponential decay, the loss goes down. And on the other hand, if they are negative, then the loss grows exponentially. This you can compare against the 0-1 loss. 0-1 loss means you have a loss of 1 if you do something wrong, and a loss of 0 when you do something right. And at the point 0, you have this jump. Now, what is interesting about the exponential loss is that even if you are somewhere here and you classify correctly, it is good if you can push out the parameters further to make your loss smaller, because that basically means your function is more decisive on classifying into a certain category. And even if you are here and you do something wrongly, you know how to change your parameters to decrease the loss. Whereas with a 0-1 loss, when you are here or here, it's the same loss and you don't know in which ways to change your parameters. So we have the exponential loss described as I said. And now this is this minimization I've showed you before. And now let's look at these terms. And the idea is that if we have this term of the previous prediction and the new added prediction, that the previous prediction can be thought of as a kind of weight. When this is the weight for the basis function m given our data point I. So this is a term that is completely fixed at this point when we look at which new basis function to define. So we don't change it anymore. That's why we take this out of this formula and say this is now our weight. And here we have one part of our loss function that we can still optimize, that we can still change. So this is this part that's taken away from this weighting. And this definition of weights we need later on. So remember, this came from here. And now, for any weight, we can say we only want to weight positively, not negatively. Because when we weight negatively, then strange things happen. Suddenly becomes better if we completely ignore it or do the contrary. It doesn't make quite sense. So we want this weight to be larger than 0. And when we want to, when we assume that this theta is larger than 0, this whole term is the same as this weight and times the yi is different than our prediction function phi tilde. Because why is this the same? I claimed that this was the case, but have not shown you. So let's show you. Because when we have this term, we can take this e to the power minus theta tilde or e to the power theta tilde. Outside of this equation, when we separate the data points into those data points that are classified correctly by the new function and those that are classified incorrectly by the new function, and they are just distinguished by different than or equal. And then, of course, depending on whether they are correctly or incorrectly, correspondingly we have positive or negative result here. And the weight is, of course, the same here, and everything else comes from taking these two aspects apart. And now, when we have this, look, we do not go over all data points here. But when we want to go over all data points here, what we need to include are the other data points. And when we include the other data points, then we basically, for this term, have to do this condition inside. So we can go from here to this condition inside. And here we have added something that we also subtract here. So this is an algebraic reformulation of the previous line. And now we can divide by the positive constant. The positive constant that we choose is the sum of all the weights. This still gives us the same argument. I mean, it would be a different numerical value, of course, but we are only interested in the argument, and the argument doesn't change. So we divide by this, and this, of course, means then that this becomes 1, and therefore we have e to the power minus theta tilde. And here we have exactly what we had before, namely the error rate. Now this was the weighted error rate for those that are classified incorrectly, multiplied with this term before. So this is this term times the normalized error rate plus this term. Okay, when we have this knowledge, now let's claim that we put the weight at half logarithm of these odds. We have used these odds before without revealing a good reason, but now comes the reason. And when is this whole term, when is this term minimal? Yeah, we look here for the argument that minimizes this term. When is this term minimal? Well, let's look for the derivation and set the derivation to 0. So take this term and derive it in order to optimize this parameter of theta tilde. And when we do this derivation, well, the nice thing here is that e to the power theta derived by theta is the same term again. Yeah? The exponential function is its own derivative. And only when we have a negative term here, it changes its sign here. But otherwise, it's the same. So these two things derived gives us this. The error rate is independent of this theta, and this derived or only changes here this sign. And we set this to 0. And now we do a few reformulations. Yeah, we can just expand this, and when we rearrange this, here is this e theta, e to the power theta, here e to the power minus theta, this becomes here, this plus times the error is this minus minus, so this is just a rearrangement from this line to this line, and then we can move this term to the other side. And then we can just take the logarithm. And when we take the logarithm of this is the logarithm of this plus the logarithm of this. Logarithm of this is this, and the logarithm of this is just theta tilde. And then the logarithm on the other side gives us a similar simplification. And now we can resolve for this theta tilde. We put this theta tilde on the other side and this on the other side. And with this, we have this term. And since we subtract the two logarithms, we can further simplify that to the fraction which is nothing else than the logodds of the error rate. So what we now know is that theta tilde is 1/2 then the logarithm of this. And when we put the weight like this, then this minimizes what we wanted to minimize, namely our exponential loss. So we have our iteratively our previous model. Now we add a new base function with a certain weighting scheme, and this weight comes from the logarithm of the odds of the error rate. And we do the update. We have at one step a certain weight. Now we do this update like this. And we can also, instead of writing it like this, bring it into this form where we do the checking whether the prediction is the same as the prediction by the base function. And then AdaBoost has a certain parameter instead of the thetas. And since this is a constant factor, to all constant factors get normalized away, so we don't care about this part. So quite some machinery for this core idea, but this core idea plays out nicely when we do always this weighting of the data points and then our base functions. And it plays out nicely when we have this exponential loss function. Now, okay, so this exponential loss is a new loss. So far, which other losses are you aware of? Neck log likelihood. Yeah. What else? It's a typical question for any exam, oral or written. And you cannot rely on some collection of formulas. You have to know this. Have to have this in your mind, because that's really core to thinking about the loss. Is really core to machine learning. If you remember one of the earlier classes, I said that minimization of the empirical loss is key to doing any training, and the core element then is the loss function that you use. Other core is, of course, what is the kind of prediction model that you use? What is the kind of optimization procedure that you use? And what is the kind of data engineering feature modeling that you use? So these are the four main ingredients, and these you have to have in your mind for any kind of exam, oral or written. So we have now looked at this exponential loss for the boosting iterations. And what is interesting here is, here we look at the training error, that we have a misclassification rate with our training data set. And at some point, the misclassification is 0. About here, 250 iterations. But when we look at this misclassification rate, the exponential loss gets still smaller. The misclassification cannot get any smaller than 0, right? When you look at the 0-1 loss, once you have classified everything correctly, there's nothing you can improve anymore. But the exponential loss decreases further. How can this be? Why is the exponential loss, why could it possibly still improve further? Because? because the weights are non-zero, yeah, the answer doesn't quite fit the question, I would say. Well, let's just look at some data point. And let's assume that we know that this data point should be classified as +1. And now with our decision stumps, let's just assume, okay, here is the first dimension, here is the second dimension. And let's assume the first decision stump would be here, and this would then classify everything in this direction as -1, so it would be wrong. And well, of course, there are more data points here and here that led to the choosing of this decision stump, these parameters. Okay, so what we do here is we do a wrong classification. A 0-1 loss would say, well, we have a loss of 1 because we wrongly classified this object. Well, just looking at this individual single object. Now, when we move this decision stump, then it would be, this object here would be classified as +1. And the 0-1 loss would say it's 0 loss. Now the exponential loss would, however, say I look at y times f hat of x minus e to the power. Let's assume that this happens to be the distance 1. Could be any number. Yeah? Then, of course, well, it's not completely correct, but anyway, let's assume this would just give us a value of, no, let's pick a value of 7. Let's assume f hat of x would be 7. And the classification of this decision stump would be +1. Then we would have e to the power minus 1 times 7. Okay, e to the power minus 7. This is a small number. But if I can shift this decision further here, then maybe this distance would become larger, and I would now have e to the power minus 1 times 21, which is an even much smaller number. Whereas the 0-1 loss would stay the same, we classify correctly. So pushing this decision stump such that the difference between these values gets larger and larger and larger allows us to make a more decisive decision. And as long as we do not increase the mistakes with other data points we have somewhere, this helps to push the decision boundary away from our data point, which is what we want for generalization. Yeah, I mean, when we have this data point here, we could also have a decision boundary here, but then a very small fluctuation of this data point would already flip it to the other side of our decision. And that would mean we don't generalize very well for this data point. While having the decision boundary far away from the data point means we have a very decisive decision. It must be in this class +1. So what we do with this exponential loss is we push our decision stumps as far away from our data points as possible to make a as decisive decision as possible. And of course, we don't do this just in consideration of one data point, what I try to do on the blackboard here, but we do it in a combination of many data points. And now we can look at how this works for all the different loss functions that we looked at so far. So misclassification is a loss function. This is a 0-1 loss. Either we are correct or we are wrong. So the sign of our predictive model is the same as our true label. I explained it now for an exponential loss. Yeah. And this exponential loss is described here in blue. So it goes steeply when we do a mistake, and it goes quickly to 0 when we make a positive prediction. We had cross entropy before, this generalization of neck log likelihood, or binomial deviance. This is the logarithm of 1 plus this in this dual case, but basically we have this cross entropy between the two distributions. And the cross entropy is in orange here. You see that the cross entropy does not go as quickly to a high loss as the exponential loss. And it does not go as quickly to 0 as the exponential loss. We have the squared error loss that we used for regression, for linear regression, for example, but also for other regression problems. And the squared error simply takes the distance between the true value and the prediction and squares it. Now, this is here, this red line. And this is optimal when, and note here, this is YF on this line. And let's assume here Y is only +1. So it's basically minimal when F hat is also exactly 1. But once F hat becomes larger, so is more decisive, then the squared error gets worse again. So this is the reason that the squared error is not a good loss function for classification. Because when you make a very large F hat prediction, this should point towards the +1 class. But here with the squared error, you would punish this very large prediction, this very decisive prediction. On the other side, the squared error is okay. It goes rather quickly when you do this mistake here to some negative error. And then we have another loss that we have not seen yet, but which comes with support vector machines, which we will tackle next, which is the hinge loss. The hinge loss is a very simple loss. It's a line that goes straight to this point and then stays 0. So with the hinge loss, you say, I want that there is a certain minimum distance from the decision boundary. Once you have reached this distance, I don't care to optimize any further. If your point is just a little bit above the decision boundary, then with the hinge loss, you say, that's not so good. Because I really want my data points to be away from the decision boundary. Now, when are these different loss functions good or not so good? You have any idea of when a loss function, what could be a positive quality of a loss function or a negative quality? It's a very hard question, but maybe think about it. What makes a loss function good or bad with a certain property? Well, we may, for example, look at the base error. Now, when we do an error that we cannot get rid of, then, for example, exponential loss punishes our loss function very strongly because we don't get rid of it. And when we try to get rid of it, because the punishment is so strong, then we may do another mistake. And this is a point where we can overfit with our boosting strategy that has this exponential loss. It pushes away, look here, exponential loss is this blue line, it pushes away strongly if I have a mistake. And that may push the function in a region where we put too much emphasis on such a Bayesian error, which is just, we cannot find any model that really is better, given the observation of our objects that we have. So here, hinge loss is often better. On the other hand, with the hinge loss, beyond this data point, I cannot optimize any further. And this here is this comparison of losses for binary classification. Yeah, and here are some of these descriptions that I just told you. And then, of course, we can also look at loss functions for regression. So where we want to predict a numerical value, and when we deviate, we want to punish because of our loss function. This is a good question whether some loss functions are better or worse when you over-parameterize. So when you have very many parameters, and then what loss do you use? I don't know about a comparison between these different loss functions then. So most observations that people do for classification are then with cross entropy. When you take neural networks, for example, where you often have over-parameterization. But I don't know that people would compare such an exponential loss against cross entropy and study over-parameterization. So I cannot give the answer. Maybe you want to do this as a thesis. Yeah? Maybe it exists. Yeah, I don't claim that I know all the literature. There's really too much literature with, I think it was like definitely more than 10,000 submissions to the last NeurIPS conference a few weeks ago. And they are all published at some point on arXiv or somewhere else. And this is just one conference in 1 year. Yeah? So I wouldn't claim that I don't know all the answers for that. Okay, so when we have loss functions for regression, then of course we are interested in y minus f. The distance between our true value y and our prediction f should be as small as possible. And it's optimal when there's a zero distance. That's quite clear. So all loss functions should have for a zero distance a zero loss. Then the loss becomes larger when you go away, either in the positive direction or in the negative. When we take the squared error, this is this orange line, we have a parabolic function. Yeah, just the squared error loss, obviously. We can also take the absolute error, and the absolute error is here this blue. Yeah, this is just this loss function here, y minus f hat. And yeah, so the drop, this has its upsides and downsides, as we discussed for regularization, where we compared lasso with Ridge. Yeah, for Ridge we had this additional punishment by squared sizes of the beta versus the absolute values. So when I do small mistakes, the squared error loss does hardly punish this. When I do large mistakes, the squared error punish this strongly. The absolute error does not punish the larger errors so strongly. Now, whether this is good or bad, that depends a bit on the data set. How many outliers do I have? And then there are combinations of the two. One proposed by Huber, which is basically like a squared error loss within a certain vicinity of 0, but then changes into a linear function. So here it's a squared error for some surrounding around 0, and above that it is just some linear deviance between y and the prediction, and then adjusted in order to fit this parabolic function around the vicinity of 0. So squared error loss emphasizes the large mistakes, is then less robust against outliers. So you have a very strong outlier. This can ruin your function, because if you put too much emphasis on the one thing, you may ignore others on which you should learn. So if you have a long-tailed error distribution, for example, that may be problematic. And here's the summary. Squared error loss and exponential loss may perform badly with such outliers, and squared error loss may perform badly with outliers, but they typically have elegant methods, and that also is often quite good. You can analyze very well when and why they work. Now, okay, what do we have? What kind of ingredients for today? We have this ADA-BUS scheme, which consists of a forward stage-wise additive modeling. Yeah, we do n steps and then improve further. It's not yet the best boosting approach, as is done in the Kaggle convolutions. The best boosting approach comes from gradient boosting, which has a somewhat similar idea, but a slightly different approach. So there's always the question how to pick these base functions. We have here with gradient boosting the same idea, that we use the highly weighted data points to guide the reduction of the loss. So we are really interested in these data points with the high weights, and then we look for the correct weighting of the correct base functions. And we saw that this can be rewritten as the weights times the incorrect classifications. Now, when we want to reduce the loss, how we can look differently at this problem is to say, what if we take this loss function that we have here and use the gradient of the loss function to reduce it? And well, we can use the exponential loss function. We can also use a different but differentiable loss function. So compared to ADA-BUS, we are actually more flexible, and we can also go away from the exponential, which has problems with being oversensitive to outliers. So again, we are given training data, and now we fit our function f hat, in this example, to fit a numerical value. So we want to fit the squared loss. And what we get are residuals. Yeah, of every mistake that we do here is nothing else than a residual, just like in linear regression. And now the idea is that in order to improve, we learn a regression tree. And that we call this regression tree h hat m of x, such that when our current model is f hat and we add this regression tree at this particular point, we better hit our target value for our regression task. So we learn this regression tree. Now no longer for xi's and yi's, but for xi's and RIM's, such that our h hat can compensate the issues with f hat, the mistakes that we do. So let's do this by adjusting f hat. In which direction? Well, in the direction that best approaches the y. What is the best direction? So let's assume our f hat of xi is a particular data point. Let's call this zi. Then our loss is described by the difference between yi's and our zi's squared. And then the direction of the greatest change, the reduction of this loss, comes when I take all the partial derivations of zi, so the gradient, and so I compute the gradient vector for this loss function. So that means I take the partial derivation of this loss in every dimension, namely with regard to all data points. I have n data points and I take all these partial derivatives. Now the sets were nothing else than the f of xi. So instead of z, I can also write f hat here and the partial derivatives of these f's, which gives me this gradient vector. A very large gradient vector because I have many data points. And here you see this is all the squared loss, and every time this partial derivation. And I basically just did this small trick here. So you see that whether I compute the partial derivative with regard to such a function value or with regard to a set is not really a difference. It's just a different name for these beasts. Now when I look at a particular entry, what is the derivative of this with regard to this? Well, this is nothing else than you take this outer function and derive it. So that's then 2 times and half given the inner function. So 2 times a half is 1. Then you have the inner function. So this is the inner function. And then you have to take this inner function and derive it. Now, if this is a variable and this is the same variable, this derivation is nothing else than -1. And this is a constant, so deriving a constant is 0. So all that remains left for this inner derivation is this minus here. So this partial derivative is nothing else than minus the difference between yi and our current computation, which is nothing else than a negative residual, or here summarized in a residual vector, the negative residual vector. So basically, this means when I do mistakes, in order to correct the mistakes, I just go in the other direction of my residual vector. Makes sense, right? It's very simple, actually. So residuals are kind of negative gradients here. So that means when I do my next stage for my modeling, I take the previous stage plus this tree. Well, this is the same as the difference. This is the same as my gradient, which is the same as my residual. And so let's assume I start with a constant function as a baseline. I iterate. I compute these derivatives. Now I have used a particular loss function, which makes it super easy. Of course, you could have a different loss function, then you would have here a different partial derivative. Can become a bit more complicated, or not, depends on what you do. And then, no matter which partial derivative you use, you fit then a regression tree to GM, Now we have to do this for all our xi's. And the way to do this then is that you define regions, you put these data points into regions, and you basically look for constant values to add to the current function if they are in such regions. And then the update is the previous stage plus region-based constant values in the case that the x is in such a region. How does this look like? And then you output the result. That's how it looks like. So here, for this function h, one can build two trees. By the way, the target function for this picture is the gray one. It's not so easy to see, but you see this gray one here has a kind of a parabolic shape in this. If you fix it to be, how to say it, if you fix the one dimension, yeah, it's a bit parabolic in this direction. If you fix it later on here, it's parabolic in this other direction, and in between you have a kind of a transition. And you try to learn this complex function with such gradient boosting. And when you have a tree of depth 2, well, let's assume this is your target. Then you have some residuals, and then you predict the next tree. For example, here you have a rather large error, so you try to predict this error. Here's another example. Tree of depth 0 is just a plane, this gray plane. The function here has this kind of funny head and then becomes large in the surrounding. The tree of depth 0 is just a plane. A tree of depth 1 then allows you to have this kind of staircase that goes in several directions for this original complex function. And as the tree depth increases, you see how you better and better approximate this quite complicated function. So what you basically here see is that gradient boosting, what it does is it looks at where do I make my largest mistakes, and in the area where I do these large mistakes, I correct it with a very simple mechanism, namely I do some kind of averaging in this area and add only for this area a kind of a constant value on top, a weighted constant value. And which leads to a little bit, I would say, here you can see it, it's a kind of a step function that you get. And of course, the more steps you have, the less it looks like being steppy and the more continuous it looks like, and the better than the approximation. And here is also a website where you can play around with this to get a little bit of feeling of how such gradient boosting models are constructed. Okay, so that's quite neat because it's a simple method, very effective, and yeah, often the go-to method when you need a good quality model, especially on tabular data. What this also shows is what you do here with bagging and boosting, you make use of small signals. And this is a core principle behind machine learning. You try to use small signals in order to improve your models. And quite often when you can find different ways to exploit small signals, then your machine learning results will be good, provided that these small signals contain some truthful content of what you want to predict. Yeah, simple stepwise fitting or interpolation is often super good. And there are, of course, many variations. And here I showed you now gradient boosting for numerical predictions for regression tasks, but you can also do this for classification or learning to rank. And I showed you the discrete ADA boost, but that exists also for numerical regression, so there are always the counterparts exist. And here's the sources, and that's it for today. Unless you have questions, I'm happy to take these. Okay, have a nice week, and see you next Monday.